All right, in this section, we're going to cover the concept of second derivative. And to get there, though, we're going to go through first derivatives and a little bit of review material, so please bear with me. So for this first problem, we're going to talk about the distance of your car from your house, and we're going to say going north, just so we give it a direction, can be measured by this function, where I'm going to say t, think of t as time measured in hours. Okay, and p is distance, so let's think of that as in miles and in the direction of north. Okay, so what I want you to do is find these values, interpret these, and then I'm going to go through the meaning in a second, but right now just figure out what do each of these things equal. And as a quick review, what I'm going to do is in my calculator, I'm going to go to my y equals, type my equation in there, then I'm going to go to my table set, and whoops, not my table, go to my table set and change my independent variable to ask. So that way when I go to my table, I can just type in the values I want and fill them out right here on the page. Okay, so you go ahead and do that, get your values either by hand or using a calculator, and then we'll talk about meaning. Okay, so you should now have your answers of 0, 6, 0, and -12. So let's think about meaning. Let's talk about what those things mean. Since t is measured in hours, okay, and the output p is measured in miles, what we're saying is at 0 hours I have gone 0 miles, because p, this is p, just a distance. So therefore you're going to say something like, for this first equation, something like, when I started driving I was at my house, or when I started driving I had gone 0 miles from my house in the north direction, however um, exact you would like to be. I'm not persnickety on it, just as long as you're displaying the concept. So you could see I wrote it as, at the start of my trip I was at home. So there you go. Or at the start of my day, whatever you want to put, I don't care. All right, so for the next one, we should say something like, after 1 hour of driving, or at the 1 hour mark, I was 6 miles north of my home. So if you're getting this, you pretty much got what I want. So let me fill out the next. Okay, so I now have the next two. So the one we talked about was, after 1 hour, I was 6 miles north of my home. Great. So the next one now, with the input of 2 and the output of 0, well, what that's saying is after 2 hours, I was back home. I was 0 miles north of my home again, so back home. All right, so for the last one, this is the key thing I was trying to work towards. Notice this one has a negative. So how do we interpret a negative? Well, if positive was north, then what would we do? Well, and so hopefully you said, well, that would be south. So then what we're going to say is after 3 hours, we were 12 miles south of our home. So after 3 hours, I was 12 miles to the south, or just south of my home. Okay, so I hope that's making sense. Hopefully that's just review. South of my home. There we go. Can't speak and write at the same time. There we go. So hopefully that's just kind of review. So now, just as a bit of review for number lines. Remember, the number line is the concept of just the x values. So what we're going to do is we're going to say we had x values at 0, 1, 2, and 3. And the really super important ones, what we'll learn as we go on, is we really need our zeros. Zeros are incredibly important. So I have a 0 at 0, and I have a 0 at 2. Now, what we're going to do from here on out, though, is we're going to say, all right, between 0 and 2, I don't really care what kind of number I had, just was it positive or was it negative? So then what I'll do is, instead of actually writing the numbers, I'll just say it's a positive. Then after 2, it was a negative. So we have the kind of idea of, from 0 to 2 hours, we were north of our home. And then from 2 hours after, we were south of our home. That kind of makes sense, and we'll prove that to ourselves in a little bit, why we can make that kind of statement later, and just we'll go with that for now, that part for now. Okay, so moving forward now, we're going to start working our way towards the second derivative, but to get to a second derivative, we first have to take a first derivative. So what I want to do is find p prime, find the first derivative of our original function. So our original function, p of t, without doing anything, was just t cubed minus 9 t squared plus 14t. So hopefully you pause the video, see if you can do the derivative, and then unpause. Let's make sure you got it right. Now hopefully this derivative was not too bad for anybody. we just went ahead and said it's all power rules. So therefore you bring the 3 out to the front, subtract 1, yada, yada, yada. So now, there we go. There is our derivatives. So now what we're going to do is find these values for our derivative. Now let me show you a little calculator way of doing derivatives. I would say this is good when you're having to substitute in a lot of values. Not so good if you just need to do one. You might just find it quicker to do it by hand. But what we're going to do is say, look, I want to do the derivative of the thing in y1. So what I'm going to go ahead and do is go to line y2 and press the math button. So I'm going to press math. Now, if I arrow down, it's option number 8. So I think it's actually quicker to arrow up, but that's beside the point. Yep. Option 8, which is n deriv. So when I hit enter, now on the new operating system, it gives me this very fancy schmancy graphic where I can fill it in. So I'm going to go ahead and say I want dx, that's the derivative notation, of what? What do I want to do the derivative of? Well, that's my y1. So we're going to press vars, or over to y vars, hit enter for function, y1, and now I'm going to do the derivative of y1. Now the last thing it's asking me, if you recognize the notation, is it's just saying what number do you want me to substitute in? Well, we want 0, 1, 2, and 3. So because we want lots of things, we're going to go ahead and just call that an x. And in our table now, we can type in our numbers, and it will, when it'll, excuse me, not fill it in for us. There we go. Well, it will fill it in for us once we type in our numbers. So do you see we've got what we want? So let's go ahead and now go to the table, and you can see, hey, the y2 line is all of our derivatives. So if I were to substitute in 0, I would get out 14. When I substitute in 1, I get out -1. When I substitute in 2, I get out -10. And when I substitute in 3, I get out -13. Now, of course, you can do this by hand. It's just a way of saving yourself a little bit of time, but do not use this in substitution of understanding. You need to know how to do it by hand. Okay, so now I want you to pause the video and think about meaning. And remember that P was measured in miles and T was measured in hours. So the derivative, I want you to think about what that derivative would mean. Okay, pause the video, think about it. Okay, here we go. So we have to remember a derivative is just the concept of slope. It's just the concept of change in output over change in input. Our output was P and our input was T. So that would be miles over hours. So it's the change in miles over hours, or AKA miles per hour. Great. So now what I want you to think about is, all right, at 0, we have a miles per hour of 14. So what does that mean? Well, it means we were traveling in the north direction at 14 miles per hour. Let me write that out. So there you go. So what I said is at the start of our trip, we were traveling north at 14 miles per hour. Now don't confuse that with the concept of average rate of change. We didn't say we were traveling 14 miles per hour for an hour. This is an instantaneous rate of change. Just right when we were peeling out of our driveway, we were going 14 miles an hour. Okay, so then what does P prime of 1, -1 mean? Well, okay, stop and think about it. Okay, so what does that mean? Well, it's a speed. It's a miles per hour again, right? So therefore, at 1 hour, we were traveling 1 mile per hour, because it still has the same units. It's miles per hour, and you stick that over 1, so it's miles over hours. Okay, so it's miles per hour. But we are now not going in the positive direction. We're going in the negative direction. So it means we're traveling south. Okay, so I'm going to go ahead and fill that in. Okay, so I went ahead and filled in the last couple, and they have the same meaning, so it's just with different miles per hours. So for like the second one, the one here, the third one, where I put it in the 2, what we're saying is at 2 hours, we were traveling south at 10 miles per hour. And it's important to remember, these are derivatives, so they are instantaneous rate of changes. So again, it doesn't mean we're traveling an average that amount of time, or that speed. It doesn't mean we're traveling that speed for an hour. It was just at that instant we were going 10 miles per hour south. Then at the 3 o'clock hour, or the 3 hours after traveling, we were going 13 miles per hour in the south direction. Okay, so now what we can do, instead of using P prime notation, a lot of times we'll switch it to V of T. And why is that? Well, remember what we're talking about. When we did the derivative, this was speed, right? This was miles per hour. And the sciencey term is, instead of calling it speed, we like to call it velocity. Why do we call it velocity? Well, velocity is the same idea as speed, except it's speed plus direction. And so what we were saying is the negatives have a meaning. They're telling us a direction. So that's why these are really velocities. So a lot of times, instead of writing a p prime for position, they just write v. So there you go. So now what we're going to do for making our number lines, what we're going to focus on is zeros. Zeros are going to be incredibly important. So what I want you to do is take your v function, the one we created from above, and we're going to figure out where it is equal to 0. So what was that function? Here it is. So I'm going to go ahead and steal it really fast. Whoops, I missed the 3. Okay, and we're going to go down here, and I'm just going to paste that and drag it on in. Okay. And again, instead of calling it p prime, I think it would make a little more sense to call it v of t. I think you guys would agree. So what we're going to say is, where does this thing equal 0? So does that mean I'm going to substitute in 0, or does that mean I'm going to set it equal to 0? Well, let's think about what that would mean. If I substitute in 0, what I'm saying is that time is equal to 0. Is that what I really want to know? Where does time equal, what is the velocity at time equaling 0? No, that's not what this is saying. If I wanted that, then it would look something like this. V of 0 equals what, right? Because then I'm saying everywhere I have a t, replace it with 0. When I set it up this way, what I'm saying is I want a velocity of 0. All right, so now we got to remember how to solve this thing. Will it factor? Can we complete the square with it, or do we want to use quadratic formula? And I'm going to say quadratic is the best way to go because it's definitely not going to factor. Because what times what makes 14, as you know, you go through that process, it's not going to factor for us. So we're going to do x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, so go ahead and fill that in, simplify, get your answers, and I will pop those up on the screen. Okay, so what I got is 2 answers because of the plus and minus. I got a 5.08. That's right, and it's not an x though, silly me, because our input variable isn't x, it's t, is it not? So what we're going to want to put here is t is approximately. All right, so there we go. So we got t is approximately 5.08 and t is approximately 0.92. So what does that mean? What does that mean? Well, what did we just find? They're t variables, so you could stick a value on them, right? That is measured in hours. So what we're saying here is the velocity is 0 at 5.08 hours or 0.92 hours. So what we're saying here is the car isn't moving. If the velocity is 0, we're not going north, we're not going south, right? We're not moving. So the car is stopped at those times. And remember, there's a couple of different things that you could attribute to stopping. It could be a stoplight, a red light, a stop sign. You could have stopped for lunch and you're eating lunch. Just something like that, right? So at 0.92 hours and at 5.08 hours. Okay, I hope that makes sense. So now let's represent those numbers on the number line. This is going to be incredibly important. We always want to make sure we represent our zeros on the number line. They're very important. So again, our values, our key values from before were 0, 1, 2, 3, I believe. Maybe we went to 4. We'll look back. Now I want to capture my zeros. Zeros were at 0.92 and at 5.8. So we might have to extend this out a little bit to, let me switch back to the green actually. 3, 4, 5. Okay. So there we go. So then my other one's at 5.08, something just past 5. Okay. Now, what I want us to do is let's fill in what our derivatives were. Let's fill in those values. So when I substituted in 0, I got out 14. That's a positive, right? So what we're going to do here is say when I got 0, this was a positive. It was a 14. Then when I substituted in something between 0.92 and 0.58, all those values in between, you see, 1, 2, 3. Do you see those are all negative values? So what we're going to say is anything between here is a negative, and we'll convince ourselves of that in just a second. Now, let's get one more value just to kind of prove to ourselves. What's going to happen if I substitute in 6? What's going to happen to my derivative here if I substitute in 6? Let's go ahead and turn that back on. Let's go down here, substitute in 6, and you'll see now our derivative is 14. So when I substitute in 6, I'm now getting out a, whoops, I want that blue. We're now getting out a positive value. Interesting. Now, what we're going to argue here is that because my zeros were at 0.92 and 5.08, I now know if I know one value in between those, if I know one of them is negative, then I know all of them are negative. And here's how we can convince ourselves of that. This graph is continuous. This graph is a parabola, right? It's a parabola opening up. Now, wherever it may be, who cares? I don't know. Not terribly interested in that. It's a parabola opening up. There's no holes, there's no breaks, there's no jumps, there's no sharp turns. It's a parabola. So therefore, I know if one value, when I substitute one value, if I get out a negative and I substitute in another value, I get a positive. Well, the intermediate value theorem says that I have to pass through every y value in between if my graph is continuous. It's kind of common sense. Think about like an airplane. If the airplane was on the ground and now it's at 500,000 feet, well, it means it had to pass through everything in between, every height in between. It can't teleport. So that's what we're saying here. One of our values were negative on this side of the zero. Another value was positive on the other side of the value. So therefore, the only way for me to get from a negative to a positive is I have to pass through a zero in between. Now, the trick to this is, how do I know there were no other zeros? Well, that's what the algebra showed us. When we did our quadratic, we saw that these were our only two zeros. So therefore, I know these all have to be negative. Then on the outsides, they all have to be positive. Okay, so what would that kind of, and what that kind of looked like on the graph, we see right here, if I drew it a little bit better, like we can do better than that, especially since we know where our zeros are. We know we have a 0 at 0.92, we know we have a 0 at 5, just after 5, and we know they're all positive on that side, all negative on that side, and there's our derivative graph. Okay, now what does that mean as far as our regular graph? What is that telling us about our values? Well, think about speeds, right? Think about speeds. What these values here are saying is if we have a positive speed, how we interpreted that before was we were traveling north. So what does that mean about our position graph? If you think about your position graph, from 0 up to 0.92, 0 up to 0.92, it means we were going up. Then after 0.92, all of our derivatives were negative, which means our graph's going south. Our curve is traveling south. So no, we're no longer going up, we're now going south. And then at some point, we know it's just after 5, excuse me, up until just after 5, our graph's going to keep going down, keep going down, keep going down. And then just after 5, at 5.08, our slope's now changed to up, which means we're traveling up. So you can kind of see that idea looks like a cubic function, right? We were traveling up from 0 to 1 to 0.92. Then we were traveling down because we had negative speeds, south speeds, from 0.92 all the way up till just after 5. Then after 5, we were traveling up again. I hope that makes sense. Okay, and you can convince yourself of that. You can look at this on your graphing calculator if you'd like. And now let's keep going with this though. Let's keep going with this because we need to get to second derivatives. So right now what we're going to do is take the derivative of v prime, and then we're going to rinse and repeat. We're going to do the exact same thing we just did. So v is right up here. It's 3t minus 18t plus 14. So what would v prime be? V prime of t, right, the derivative of that would be 6t minus 18, right? Okay. So once again, let's find our derivatives. Well, let's find our values. We go ahead and substitute these in, and that shouldn't hopefully be too hard. So that's negative 18. And I'll go ahead and fill these in, pause the video and fill these in. And you do the same. Okay, so hopefully you noticed that this is linear. So therefore we have a slope of 6, so our numbers are just kind of going up by 6. So just to convince ourselves though, if you need one more, let's throw in a 4 there. And so if you substitute in 4, that's 12, 24, 24 minus 8. Oh, that's 6. All right. So describe the meaning. Now this is the hard one because this is a little abnormal for us to think of. Describe the meaning. What does this mean? Change in velocity over change in time. Well, what is that concept? Change in velocity. Well, velocity is speed. So if I'm talking about how my speed is changing, right now I'm at 2 miles an hour, and then later I'm at 12 miles an hour. Well, the word we tend to use for that is acceleration, right? We say are we speeding up? Are we slowing down? Acceleration, deceleration, and we'll get into that in a minute. But the concept here is your acceleration. Okay, so instead of using v prime of t, instead we tend to use a of t to do acceleration, right? And what does this mean? What does this mean when we talk about negative 18? Well, it means our speed was changing at 18 miles per hour per hour. Oh my gosh, that's a mouthful. But if you think about it, our velocity, our speed, is going down. We were going faster. Now it's going more in the negative direction at a rate of 18 miles per hour per hour. Because when you think about your units, dv is measured, velocity is measured in miles per hour, and then it's over time, which is measured in hours. So there's your miles per hour per hour. All right, we'll get more into that. I'll make it easier, I promise. Okay, so now, just like the last problem, zeros are important. So go ahead and find for me, take your velocity equation, which was 6t minus 18, or sorry, your acceleration equation, which was 6t minus 18, and go ahead and solve that. Find your zeros. And as we talked about before, do you substitute in 0 or do you set it equal to 0? Well, we're going to set it equal because otherwise it would be a of 0, right? So we'll go ahead and do that. And when you solve that out, that's going to give you what? T equals, add the 18, divide by 6, so that's 3, I do believe. Oh, wait, we already knew that. That's sitting right here. Oh, there's our 0. But we've now convinced ourselves there's only 1. Because it's linear, there's only 1 of them. So describe what this means. Describes what this means. If our acceleration is 0, what does that mean? Our velocity is not increasing, nor is it decreasing. It's not changing. Our velocity is constant. Oh, so that just means we're going the same speed. So it doesn't mean that you're standing still. It just means that your speed is not changing. We were going 65 miles per hour. We're still going 65 miles per hour. So what we can say is that we're traveling at a constant speed at 3 hours. So at 3 hours, our speed wasn't changing. Constant speed. All right. So now, here we go. Number line once again. 0, 1, 2, 3, 4. And I'll take it out to the 5. Okay, just because that's what we did before. And now what we can see here is we're traveling at a constant speed at 3 hours. 3 hours was our 0. That was the important point. So I'm going to go ahead and put that on the graph. Okay. Now, when you think to the left, what kind of accelerations did we have? When we were plugging in 0, 1, 2, those were all negative values, right? So we'll go ahead and say anything from here is a negative. Then to the right, that's where we get positive. So therefore we know we have negative accelerations to the left and positive accelerations to the right. Now the easiest way for me to describe positive and negative acceleration is if we think about negative, if you think about that's gravity, okay? Gravity is always trying to pull you down. So no matter what you're doing, if you think about throwing a pen up into the air, as we throw it up, the speed at which we're going starts off fast, and it slows down, and then because gravity's always trying to pull us down, right? But if you have a positive acceleration, you can think of that as a big fan, and the fan is trying to blow you up. So you can imagine you're falling down, but there's this fan down here and its blades are spinning and going shh. And so now as you're falling towards it, it's slowing you down, and then trying to eventually push you back up. So positive accelerations push upward, negative accelerations pull you down. Okay. And then once you get more comfortable with it, we could extend that to brakes on your car and stepping on the accelerator in your car, that kind of thing, the gas pedal. So, nonetheless, we're going to put this all together now. What we're going to do is look at the original graph, and we're going to compare all these number lines and things and kind of see what's going on. So let's go ahead and get a graph up of our original function. Okay, so what you can see here, I've done the graph of our function, and just for the window, if anybody wants to mimic this on their calculator, I made my x values for the window go from 0 to 5, and then for my y values I let them go from negative 50 up to positive 20, or maybe it was 10. I think it was 10, positive 10. And so what we're seeing here, if you look at the thin line, that is our position function. That's the original cubic, and you can see it having that cubic behavior that we're talking about, where rising up, then coming down. Okay, and then for our velocity graph, that's the thick line. That's the one I'm highlighting here in blue. So let's look for the relationships that we were talking about. Now, velocity, if it's a positive velocity, right, above the axis, that means our graph should be going up, because if we have a positive velocity, if our velocity is 7, that means we're traveling north 7 miles an hour. So, and that's what you can see. As long as our velocities are above the x-axis, our graph is going up. Then, once our velocities go negative, you can now see they're all below the x-axis. Everywhere we're below the x-axis, you look at our graph and our graph is going down. It's going down, it's going down, it's going down. Then once our velocity gets back to the x-axis, you see our position graph is now leveled off. So we can see all of that fitting, right? It's pretty awesome. So now, how does the acceleration graph fit into this? Well, it's a linear function, we know, that's traveling through 3. It has a 0 at 3, and then actually, yeah, and then it's going to look something. It's just a linear function. It's going to come through like this. So what does that look like to us? What is that saying? It actually may be a little more steep than how I drew it. Maybe a little more like that. So nonetheless, what is this saying to us? When we have negative accelerations, that means gravity is pulling us down, right? But then when we have a positive acceleration, that means the fan is blowing us up. So think about what we're saying here. Think about the pen. As long as we have a negative acceleration, as long as this line is below the axis, it means gravity's pulling you down. So if you're a pen being thrown up into the air, if you're trying to go up, gravity's going to slow you down, slow you down, slow you down, slow you down until it eventually wins, and now it's going to start pulling you down faster, pulling you faster and faster. And notice how our graph's getting steeper and steeper and steeper and steeper until we hit 0. Now, once we hit that fan, instead of gravity pulling us down, now the fan's trying to blow us up. It's trying to blow us up into the air. So instead of getting faster and faster going down, now we're starting to go down slower and slower and slower. Now we're still falling. We're still going towards the fan, but the rate at which we're falling is slowing down, slowing down. So if we know acceleration is going to be positive from here on out forever, what do you predict is going to happen next with our graph? So stop and think about that and say, okay, well, if the fan's going to be blowing us up and it's won the battle, it's stopped us from falling, well, then theoretically the fan should start pushing us back up. And you can see that's what the cubic looks like. It fits what we're imagining. So now, it's very inefficient to have to draw graphs every single time, right? It's not exactly the model of I'm gonna draw graphs and figure this all out. That seems like a lot of work. So instead, what I'm gonna do is I'm gonna show you how to look at your number lines to figure these things out. So, and it's all based around the zeros. The zeros are the key. So remember on the velocity graph, we had a 0 at 0.98-ish, I think, and we had another 0 at 5.08, something like that. Maybe it's 0.91. Then on our acceleration graph, we had a 0 at 3. Now, here's where it's all going to kick in. Here's where the magic kicks in. What we're going to do is break up our graph. We're going to break up our number lines by everywhere we had a 0. Now notice we're not using the position graph for this decision process. All we're doing is using the acceleration and the velocity. Okay. Now, what we're going to do is go through and fill in pluses and minuses. We're going to fill in what our graphs were. So if you need to, you can go back and look, but I've got the graph I'm going to use right here. Our velocity graph was the thick one, and to the left of 0.9, we were positive numbers. Then to the right of 0.9 all the way up to the 0.5, sorry, not the 0.5, the 5, we were negatives. We were below the axis. So this was a negative, because it's between those zeros. Then after 5, we went to positives. And if you want to verify that, you can go back and look at the original number line we did. Now for our acceleration, that's the straight line I drew, and we have the acceleration graph right here. We see it was negatives on the left, positives on the right of 3. So therefore, I'm going to go ahead and fill all this in. I had negative here. Actually, I'm not going to use red though. Negative here, negatives on the left, and positives on the right. So now, how we read this, how we're going to talk about this, is the whole concept of Is the graph increasing or decreasing? And we see that just from the velocity, right? We said if it's a positive, it means we're going north, we're going up. If it's a negative, it means we're going down. So we can immediately start by just filling that in. The velocity is positive, so it means our graph is increasing, okay? For the next box, because our graph is negative, it means we are decreasing. Similarly here, for this one, since it's negative, again, it means we are decreasing. And for the last one, since our velocity is positive, it means we are increasing. Okay, because that's just talking about, is your graph going up or is it going down, right? So now, when you look at the rate of increase or rate of decrease, that's where the acceleration is going to kick in here. And it's easiest to try to get this in your memory once you see all four of them filled out. So the idea here is, if you look at the original graph, yes, the yellow line is increasing up to 0.9, but it's increasing at a decreasing rate. Okay, don't try to make any rules in your head about how to read this until we finish them all. Okay, so we're increasing at a decreasing rate, and why is that? Well, you look, the graph's going up. It's going up, but the rate at which it's going up is getting slower and slower and slower and slower until it stops going up and then starts going down. Now we're decreasing. We start off decreasing. If you look at the tangent lines, we start off decreasing very slowly, slow negative, little negative, but then as we get steeper, further and further, it gets steeper and steeper. So we are decreasing, we are going down, but we are doing it at a increasing rate. The rate at which we are decreasing is actually going up. We're going down faster and faster and faster and faster. Then after we reach this point right here, instead of getting faster and faster, we're still going down. We're still going down, still going down. But the rate at which we're going down, if you look at all those tangent lines, they're getting less steep. They're getting less steep until eventually we hit zero. So we're decreasing at a decreasing rate. Okay. Then finally, if you imagine this to continue, you would see our graph is going up. We are now increasing. And the rate at which we're doing it, we start off slow, but then we're getting faster and steeper and steeper and faster and faster. So we're increasing at a increasing rate. Okay, so how do you see this without having to look at the graphs? Well, the idea here is, think about velocity. Velocity is talking about what direction you're going, you are actually going. And acceleration is talking about which way you're trying to go. So if we're going north, but acceleration is trying to make us go south, we're going to slow down. It's pulling us the other direction. So therefore, we are increasing, we're going up, but gravity's pulling us the other way. It's trying to make us decrease. So because these things do not agree, that is why we're at a decreasing rate. So you'll look the same idea here in this third column right here. We are going down, but the fan is trying to push us up. So therefore, once again, we are decreasing because our velocity is going down, but we're doing it at a decreasing rate because the fan's trying to push us up. They're fighting each other. Now, when you get increasing rates here in column 2 and in column 4, where you get your increasing rates is when they agree. I am going down and velocity's down and acceleration is pulling me down. They're working together. So therefore the speed I'm going is going to get faster and faster because acceleration is making me go faster and faster. Where similarly, they're working together in column 4. I am increasing, my graph is going up, and the fan is pushing me up, so I'm increasing at an increasing rate. So how do you talk about acceleration or deceleration, speeding up or slowing down? Well, it's really a comparison of both things. You can't just look at one of the values and say, if you talk about if you're speeding up or slowing down, you need to know about both. What is my current velocity and what is my acceleration? If they disagree, I'm actually slowing down. I'm doing it at a decreasing rate. Where if they agree, I am speeding up. I am doing it at a increasing rate. So that's how we can talk about those. Okay, now there's one little piece and then we're all done. One more piece and we're all done. Okay, what I want to do is I want to talk about the idea of concavity. And to do that, I'm actually just going to go back to the original graph. I'm going to get rid of my velocity graph. So I'm just going to go ahead and grab that real fast for you guys. I'll pause the video while I do that. Okay, so now we're looking at our position function. This is just the original position function, okay? And what we're going to talk about is concavity. So there's an idea of concave up or concave down. So we can either be up or down. And how we remember the general shape is kind of easy. When we're happy versus when we're sad. When we're happy, we're positive. When we're sad, we're negative. And what you can see here is concave up has the shape of the happy face. So if you imagine kind of breaking this graph up into two halves, you can see to the right hand side this is resembling a happy face as we come through here, right? You can say, if you're shading this, you would say, hey look, it's kind of, I'm making half of a happy face. Where concave down is the upside down part. It's the sad face. It's negative. Okay, so therefore concave down would be the left hand side, where if you say I'm shading it and I have a downward kind of sad face there. The other way, and it's hard for me to demonstrate on the computer, but you can imagine curling your fingers. If you are curling your fingers around this curve, you would be pouring water out. If someone poured water on it, would just be rolling off your hands. Where then as you curve your fingers, as you trace the graph on this way, you'd be catching water. You'd be holding it. So the positive catches water, negative dumps it out. Now, why is the negative and positive really important? Well, the other way we can see it is by looking at second derivatives. When I look at the second derivative values, a concave up is positive, or I'll write it as the concave up, the second derivative is greater than 0, it's positive, where a concave down would be negative, it would be less than 0. So you can see that if you look back at the original second derivative function we did, what we can see is, look, all these values over here, these all had negative accelerations. They were negative second derivatives. So therefore, we know our graph should be concave down from 0 to 3. And then it should be concave up because we had positive values from 3 to wherever. So, and we can see that concave down from 0 to 3, and then concave up from 3 to whatever. Now, this point here in the middle is a really important point. This is called the point of inflection. And what a point of inflection is talking about is, and this is key, you got to catch this, it means a change in concavity. Okay, so it doesn't mean that the second derivative is equal to 0. This fact that the second derivative was equal to 0 there means that we want to check for an inflection point, but it doesn't guarantee it. To guarantee a point of inflection, what we have to do is make our second derivative number line. So we make our number line and we say, look, I had a 0 here, which means I have a chance that this could be an inflection point. Maybe, maybe not. Okay, I'm going to put a question mark next to that. I don't know. Is it a point of inflection? Well, then we check our values. If it's negative on one side and positive on the other, then we had a change of concavity, which means we have an inflection point. And when we get to some word problems, we'll get why those are actually important. Okay, so what was the big ideas in this lesson? What were the big takeaways? We need to be able to talk about the graph. We need to be able to look at first derivatives, look at second derivatives, and understand what positive values mean and what negative values mean. So if a positive velocity means your graph's going up, negative velocity means your graph's going down. And to be able to figure out where our intervals of positive, where we need to check for positives and negatives, means we need to first find our zeros. So we go through the same process for first derivatives and second derivatives for velocity and acceleration. You still first start by finding your zeros, and then you do test points. Do I have negatives or positives? And then we need to interpret those. So big ideas: understanding how to find our zeros, then determining is it positive or negative intervals, then being able to interpret that. Means my graph's increasing or decreasing, and at what rate it's increasing or decreasing, and then finally finding your inflection points and knowing what an inflection point means. It means that we have a 0 in our second derivative, and numbers to the left of it and numbers to the right of it, not numbers, but the accelerations, the second derivatives, are different signs, negative on one side, positive on the other, because then that means you have a change in concavity. All right, happy lesson. Hope the